Good morning, everybody. You guys can't hear my music, can you? I have no idea what happened. I did not do anything. I literally did not do anything. So, it makes me sad. Okay, fine. You'll just listen to me talk. If you want to listen to the music, you can just go to the royalty-free playlist on YouTube Music. Granted, I don't have ads, though. Okay. Good morning. How is everybody? Good morning, JR. Morning, Joey. Morning, brain fog. I hope you guys all had a good weekend. Lots and lots and lots of discussion on Discord. I answered so many emails, so many direct messages. But it looks like things are coming together for the project, which is good because it's due tonight, in case you didn't know. Sorry, I'm just getting ready for this morning. I am so not ready for lecture. I shouldn't be saying that. I'm ready for lecture. I can talk about the material, but I know there's a glare. Oh, that's because, what is that from? What is something wrong with my camera? Nope. It's from my window? There we go, that went away. That was weird. Nope, didn't go away. Where is this coming from? Where is this coming from? I feel like I'm failing this morning. Important things. Get lecture going. Yeah, Joey, you can complete the quizzes whenever. That's fine. Not a problem. Why am I failing today? Oh my goodness. Okay. It's gotta be from my window. Yeah, I don't have the curtains closed all the time. Figured out the glare situation. Oh my gosh. Okay. Sometimes Monday morning just gets you. Well, I spent yesterday looking at responding to Discord, cleaning my house, doing laundry, all of that fun stuff. And by the time it got to the evening, I was like, I don't want to prepare for lecture. I'll do that tomorrow morning. And usually it's not a problem, but for some obscure reason, today I could just not figure out math. So we'll see how today goes. Like I said, I can talk about things, but hopefully I don't have too many math mistakes. No problem, Jada. Yeah, hopefully you guys are working through the project. Should be good. A lot of you guys got so far. Very impressive. Lots of discussion on Discord. I was very excited to see all of the good collaborations going on. I've just been so happy. Love you guys. I'm so proud of you guys. You guys have been learning so much. So, okay. So, let's go ahead and start. We'll see how long today takes. We'll see. So the videos for this week, if you haven't watched them, there's a little bit more just because we're covering two topics. Today, we're covering linear independence or linear dependence. And then on Wednesday, we're going to cover eigenvalues and eigenvectors. These are two relatively short sections, hence the reason why we've got 2 in 1 week, to finish up our last set of material. So this is the last set, which is awesome. Next week, we will do review for the exam. Speaking of the exam, so we met as instructors on Thursday. We put the exam together, all of that fun stuff, and the exam will not use Lockdown Browser. You will have, it's open note, open book. You'll have access to all your material. You'll have 2 hours to complete the exam and submit it. So keep that in mind. When you scan in, make sure you have your scanning process down so that you know how long it's going to take you to do it. There are going to be 6 questions on the exam, all linear algebra based stuff. You will be able to use MATLAB, check your answers. The questions are going to be designed so you can't just plug it into MATLAB. You'll need to solve for something and then you can check if you got it right. And we'll go over questions like that for review next week. But I just wanted you guys to be aware of what you have access to for the exam. Open note, open book. You will be able to use MATLAB. And we'll do a review next week. Okay, so that's clarified. Just let you guys breathe a little bit with the exam. Yeah, let's get into this material. So like I said, we are going to cover linear dependence, independence today, eigenvalues, eigenvectors Wednesday. So when we're talking about linear dependence and independence and this set of material, it's much more theoretical. We're really trying to approach, given a system of equations, how can we determine what kinds of solutions we have? What type of system is it? So in general, when we have a system of equations, we need n equations and, let me rephrase that. Generally, when we have a system of equations, let's say we have 3x plus 7y plus 2z equals 4, negative 2x plus 4y minus z equals 7. Generally, in order to solve our system of equations, we need the same number of equations as we have unknowns. So generally, here I have 1, 2, 3 unknowns. I need 3 equations. I can have more equations, that's fine, but I at least need the same number of equations as the same number of unknowns, which is why when we write our system in the form of ax equals b, when we write it like this, A is a square matrix. So we need the same number of equations as we need unknowns. Remember, our rows in A correspond to our equations, and the columns in A correspond to our unknowns. So in your project, when you are writing ax equals b, A is your m by m, which means you have m equations, m unknowns, 201 by 201. That's why A needs to be square in order for your system to be a system of equations. So this chapter takes that one step farther. This chapter is saying that you don't just need the same number of equations as unknowns. This chapter states that we need the same number of linearly independent equations as we have unknowns. So if you look at a couple systems of 2 by 2, let's say we have 2x plus 2y equals 4 and x plus y equals 2. These are technically 2 equations, 2 unknowns, but it's really the same equation. If I just divided this one by 2, it's really x plus y equals 2. So in reality, this isn't a system of equations. I cannot solve for x and y given these 2 equations, even though there's 2 equations, 2 unknowns, because it's the same equation twice. So it's not enough just to have 2 equations, 2 unknowns. We need 2 linearly independent equations to solve for 2 unknowns, or we need 3 linearly independent equations to solve for 3 unknowns, or 4 linearly independent equations to solve for 4 unknowns, etc. And that is what this chapter is approaching. Okay, so, that's great, that's fine and dandy, but why do we even care? Why does this help us? Because it gives us an indicator identifying how many linearly independent equations we have gives us an indicator of what kinds of solutions we can have and where our solution might exist. And we're talking about, no, that's not right. Not where our solution might exist, but yeah, where our solution might exist. Okay, so there's a lot of terminology in here, and I'm trying to figure out how to get us to span. Like I said, I was not overly prepared for today. I apologize. So one of the things that this chapter introduces is this idea called span. Span. There's a lot of text in there from the video. But I want to talk about span for a minute, because it's kind of going to guide us for our problems. Okay, so span is one of those theoretical concepts that's harder for students to understand. And I put together this equation, I guess, for you guys to figure out span. So here's your steps. First, we want to find the number of linearly independent vectors. And then our span is the set of the number of independent vectors in a specific space. So we're talking about vectors when it comes to span, but in reality, we're thinking about our equations as vectors. So if you look at the equation 3x plus 7y plus 2z equals 4, I can write this as a vector of the coefficients, 3, 7, 2, or I can also write it with my b value as well, 3, 7, 2, 4. So when we're talking about an equation, I can talk about it as a vector as well. So when we say vectors, think about these as equations. So span gives us an indicator of where our solution space might be. So when we talk about a space, we're literally talking about a 3-dimensional space, a 4-dimensional space, a 5-dimensional space. When we look at a vector, it contains a given set of numbers. So if you have 3 numbers here, this vector lives in a 3-dimensional space, or it lives in R3. These essentially are the same. R3D, R3. This vector has 4 numbers, so it lives in a 4D space. We can graph this theoretically in a 4-dimensional space or in R4. And so these are the same. 4D, R4. So when we talk about the span, we're talking about essentially a dimensional space in another dimension. It could be a 1D space in R1, which is literally just a line, 1 dimension's a line. We can talk about a 2D space in R2, which is the entire XY plot. We can talk about a 1D space in R1, which is just a line on a graph. We can talk about a 2D or a 3D space in R3, which is literally our entire 3-dimensional space. We can talk about a 2D space in R3, which is a plane. If I can draw 3-dimensional space, let's see if I can draw a 3-dimensional space. There's my 3D space. We'll talk about a plane. Or a 1D space in R3, which would just be another line. So when we talk about these spaces, we're literally talking about like a 3-dimensional or a 2-dimensional or a 1-dimensional like bubble. So a 1-dimensional space is a 1D line. A 2-dimensional space is like a flat plane. A 3D space is like a cube. And then a 4D space, 5D space, all of that other spaces. You can't really visualize what that looks like. But that's what we're talking about when it comes to a space. So when we talk about vectors and span, the span of a set of vectors tells us where our solution might exist. Is our solution only on a given line? Is our solution only in a given plane? Is our solution anywhere in 3-dimensional space? So like I said, these concepts are much more theoretical, but I wanted to try and help you visualize a little bit about these spaces. Now, if you don't understand everything, that's fine. This is your nice formula for span. And we will fill out this formula in a minute. Okay, so I wanted to highlight that. Okay, so our first problem, our first example, to go over today is to determine the span of a set of vectors. So span of a set of vectors. V1 looks like this. My pen. V2 looks like this. And V3 looks like this. Once again, we can think about these as equations. We can think about V1 as an equation, negative 2x plus 3y plus negative 2z equals some constant. Doesn't matter what that constant is right now. We can think about V2 as 3y plus 3z equals some constant. And then this third equation as negative 2x plus 5z equals some other constant. So we can think about these vectors as equations. And we're asked to find the span of the set of vectors. So when we talk about span, once again, we're really talking about where the solution might exist. Okay, so there's a couple ways, or the process to find span is first we need to figure out how many linearly independent vectors there are. So the number of linearly independent vectors. There's a couple ways to figure out linear independence. The first one is to set up our vectors as a linear combination. So I can set it up as C1, and we've done this before, C1 V1 plus C2 V2 equals V3. It doesn't matter the order of the vectors. I'm just going to set it up as a constant times a vector plus a constant times a vector plus a constant times a vector, equals another vector. So when I do that, I end up with this. C1 V1 plus C2 V2 equals V3. And I could have done C1 V2 plus C2 V3 equals V1. It doesn't matter. But I set it up as a linear combination, and then I solve for my constants. So this first equation, if I multiply through, no. I get negative 2C1 plus 0 equals negative 2. This tells me already that C1 equals 1. This second equation tells me that 3C1 plus 3C2 equals 0. If I plug in my 1 here, it's going to tell me C2 equals negative 1. And then I can use this last equation just to confirm those. So negative 2C1 plus 3C2 equals 5. If I plug in my 1 here and my negative 1 here, it equals negative 5, or it equals 5. Negative 5. There should be a negative. There we go. So it just confirms. Okay, so it turns out that if I have a negative 2 minus, or negative 1 V1 minus 1 V2, I end up with V3. And that's kind of obvious if you examine those. But this tells me that these vectors are linearly dependent, which means that I can use other vectors to get another vector, which means I can have C1 times V1 plus C2 times V2 equal to V3. It means one of my vectors is a combination of the other vectors. And so that means they are linearly dependent. That is one of the ways that we can figure out if our vectors are linearly dependent or independent. If I ended up with C1 equal to 0 and C2 equal to 0, so if all of my constants end up being 0, then they would be independent. So that's how we would interpret our solution if we set them up as a linear combination. If we end up with non-zero values for C1 and C2, then they're linearly dependent. If we end up with only 0 values for our constants, they're linearly independent. Okay, so difference, independent versus dependent. Okay, that's the first way I can figure out linear dependence or independence. The first way, 1, set them up as a linear combination. The second way I can figure out if my vectors are linearly dependent or independent is to put them together in a matrix. It doesn't matter if you put them in as rows or columns. I will put them in as columns because they're written as columns. So my first vector was, and I can put them in any order. I know what I'm doing, so I'm going to put them in a specific order. -2, 0, -5. So here's my vector 3, v3, and then 0, 3, 3, v4, or v2, and then v1, 2, 3, -2. So we put them in together as a matrix, and then what we are going to do is we are going to reduce this matrix to REF. So we're going to do Gauss elimination on this matrix. Okay, so let's go ahead and do this. So first, I'm going to take row 3, and I'm going to say 2 times row 3 minus 5 times row 1. When I do that, if I multiply row 1 by -5, I get 10, 0, 10. If I multiply row 3 by 2, I get -10, 6, and -4. So I end up with row 1 doesn't change, row 2 doesn't change, and row 3 now becomes 0, 6, and 6. Okay, so I made this one a 0. Now I want to make this one a 0. By saying row 3 equals row 3 minus 2 times row 2. So we multiply row 2 by 2, or by -2, I get 0, -6, -6. And then this just stays 0, 6, and 6. So -2, 0, -2, row 1 doesn't change, row 2 doesn't change. And row 3 now becomes 0, 0, 0. I'm done. Notice I end up with a row of zeros here. That's fine. However it ends up, not a problem. Once you get into REF, then you find what's called the rank of the matrix. The rank of the matrix is the number of non-zero rows you have after you reduce a matrix into REF. So here, this one has non-zero numbers, this one has non-zero numbers, and the bottom one doesn't. So my rank of this matrix is going to end up being 2. So the rank of a matrix, we put all of our vectors into a matrix, we can reduce it to REF. Rank ends up being the number of non-zero rows we have after we reduce to REF. And the rank tells us the number of linearly independent vectors there are. So I've got V1, this one's V1, this one's V2, this one's V3. So I put V1, V2, V3 in a matrix. My rank of that matrix ends up being 2, which tells me that there are 2 linearly independent vectors in my matrix. So there's only 2 of them, which means that all 3 of them, so all 3 vectors in my matrix are linearly dependent. So this is another way I can determine if my vectors are linearly independent or dependent. Put them into a matrix. It doesn't matter if they're rows or columns. Reduce that matrix using Gauss elimination. Get to REF, row echelon form. And then find the rank. The rank is the number of non-zero rows is the number of non-zero rows. So if there are 3 non-zero rows, then that means all of your vectors are linearly independent. So if you have 3 vectors, 3 non-zero rows, they are all linearly independent. Here I end up with 2 non-zero rows, which means that all 3 of them are dependent, only 2 of them are linearly independent. And that's the second way to find linear dependence. The third way to find linear dependence is you can find the determinant of A. Note this only works for square matrices. Matt, the H1 line is the first comment, the short description of your function. So Joey, if you got a rank of 3, then you would have 3 linearly independent vectors, which means they are all linearly independent. So JC, so if 2 of them are independent, all 3 of them are dependent. Remember, when we talk about linearly dependent, that means that you can get to 1 vector, or 2 vectors, or 3 vectors, by writing them as a linear combination. So if you remember back to this first example, we can write it as v1 minus v2 equals v3. So that means v1 and v2, or v1 and v3, or v2 and v3, any two of them would be linearly independent, but all 3 of them are linearly dependent. So v1 and v2 would be independent, but v1, v2, and v3 are dependent. So just like if we have a set of equations, if we go back to our 2x plus 2y equals 4, and then x plus y equals 2. Here we have 2 dependent equations, but each of them are independent. And the same idea if we had a 3 by 3. 2x plus 2y plus 2z equals 4. X plus y plus z equals 2. And then let's say we had 3x plus 7y plus z equals negative 9. These 2 are clearly the same equation. It's just this one and this one, they're just a scalar multiple of each other. So these two would be linearly dependent, but these 2, the first one and the last one, would be linearly independent, or these 2 would be linearly independent. So all 3 of them are dependent because one is just a multiple of another. I could rewrite these as 0 equation 3 plus equation 2 equals equation 1. So 2 of them would be linearly independent, these 2 or these 2, but all 3 of them are linearly dependent. So when we're talking about linearly independent and dependent, another way to think about it is how much information you are given. So here, with this system here, with this first one here, we are given really one piece of information. We're really only given that x plus y equals 2. That's it. That's all the information we're given, even though we have 2 equations. They just say the same thing. Same idea down here. We have 3 equations, but we're really only given 2 pieces of information because these 2 pieces are the same thing. Over here, it's the same idea. It's less clear. It's less clear because we can't easily see that v1 is like 2 times v3. But it's the same idea. In reality, one of these vectors is just a repetition, is just a repeated information from the other 2. So 2 of them are linearly independent, which means we have at least 2 pieces of information that we can use. The third one, if we put all 3 of them together, they're linearly dependent because we're only given 2 pieces instead of 3 pieces. The third one doesn't add anything, it just repeats what we already know. Okay, so if we want to figure out if vectors are linearly independent, we can write it as a linear combination like we did here. We can put them into a matrix and find the rank by reducing to REF. The third way we can do it is by finding the determinant of the matrix. So note, this only works with square matrices. So once again, I can put all of my vectors into a matrix. -2, 3, -2. Once again, the order doesn't matter. 0, 3, 3. And it also doesn't matter if they're rows or columns. I could put these as rows. So I could say -2, 3, -2, and then 0, 3, 3, and -2, 0, -5. So now they're rows. This is V1, V2, V3. So the third way I can figure out if my vectors are linearly independent or dependent is by putting them all into a matrix and then finding the determinant of this. So determinant of this matrix, I'll call it A just because we use A a lot as matrices. And then in order to find the determinant, I can use a variety of methods. I could use cofactor expansion. I could use my shortcut method because this is a 3x3, or my modified fish method really is what it is. I'm going to use that one. -2, 3, nope. So I just copy the values of A, copy and paste them next to each other. Copy, paste. So convenient. Okay. Then this diagonal ends up being 2 times 3 times 5, which is 30. This diagonal ends up being 3 times 3 times -2, which ends up being -18. And this one ends up being -2 times 0, or 0. So my first set of diagonals is 30 minus 18 plus 0. I'm going to move this down a little bit. My second set of diagonals going the other direction. This one ends up being -2 times 3 times 0, which is 0. This one ends up being 3 times 0 times -5, which is 0. And this one ends up being -2 times 3 times -2, or 12. So my other set of diagonals ends up being 0 plus 0 plus 12. Yep, Joey, you can use any method to find the determinant. It doesn't matter what your determinant is going to be. So, determinant of A, 30 minus 18 is 12, minus 12 ends up being 0. So my determinant of A ends up being 0. Okay, so now we need to interpret this. If your determinant of A ends up being 0, that means your vectors are linearly dependent, as you may have guessed. If your determinant of A ends up being anything other than 0, then your vectors are linearly independent. So we have 3 methods. Yes, so JR, absolutely. Yep, so here's that connection between your rank and your determinant. If you end up with that row of zeros, your determinant is going to be 0. And once again, with the rank, I put them in as columns. With the determinant, I put them in as rows. It doesn't matter whether or not they're rows or columns. Okay, so the whole goal of this question was to figure out if, yep. So yes, so you can use a determinant to figure out if they're linearly independent or dependent. Okay, so the whole goal of finding linear independence was to find the span of these set of vectors. So given, whoa, that was crazy. So given a set of vectors, if you are asked to find the span, you need to first identify how many linearly independent vectors there are. So if you're talking about the number of linearly independent vectors, then you really want to use the rank. Because in reality, we could have ended up with 2 rows of zeros, so that there's only one linearly independent vector in this set. But we need to figure out how many number of linearly independent vectors there are. Then, the second thing we do is we want to use our span formula. So the span of a set of vectors is a blank D space in R blank. This first blank is the number of linearly independent vectors there are. So this number goes right there. This second blank is the number of elements there are in your vectors. So for this set of vectors, these three we've been working with, the span of these three vectors is a 2D space, because two of them are linearly independent, in R3, because they each have three numbers. So my span is a 2D space in R3. So there's my formula. This is the number of linearly independent vectors, and this is the space my vectors live in. The number of numbers in my vector. Each of these have three numbers, so therefore they live in R3, or a 3D space. Which means that as a system of equations, if I wrote these vectors as a system of equations, I'm really only talking about a plane. The solution to that system of equations really only exists in a plane, or at least that's the amount of information that I'm given. I don't have enough information to really get an actual solution. My solution really exists in just that plane. So that's how we can find the span. Okay, so why do we care? Yeah, I'm going to skip over that example. Okay, so the main reason why we care about this idea, about these concepts, is because we really want to know how this affects our systems of equations. So if I look at the bottom of the notes from this week, all the way at the bottom, there's this question here. There's this table I like to illustrate. So Joey, you always have at least one linearly independent vector. If you're given an equation, you have at least one set of information. So your span might be a 1D space or a line, but you're at least always given at least one piece of information. It's just, if you have only one piece, then every other piece is just going to be some combination of that. Yes, because, so will the determinant equal 0? So if the determinant is equal to 0, then that means your vectors are linearly dependent. I'm a little unclear of what you're asking. With that, yes, the determinant can equal 0. So the determinant equals 0. Okay, so that's the determinant equals 0 tells us whether or not our vectors are linearly dependent or independent. That's it. It just tells us if they're linearly dependent or independent. When we're talking about span, it's a blank D space in R blank, or in this instance, R3. This comes from the number of linearly independent vectors. So the determinant tells us if all of them are independent or if they are dependent. It doesn't tell us how many independent ones there are. The rank tells us exactly how many independent there are. What chart? I'm talking about this chart, JR. So here's a chart that I put together. I put this together, I think, the first year I taught. It just helped me. It helps me understand what this means. So if we have vectors in R2, we have vectors in a 2D space, so 3, 4. Then we have two options. There's either one of them that's independent, or both of them are independent. So if only one of them is independent, if the other one is just a multiple of, if we have a 3 and 4 and then 6 and 8, I have two vectors, but there's clearly only one vector, then my span is a 1D space in R2, or just a line. If both of them are independent, let's say I have 6 and 9, these are two different vectors, then I have a 2D space in R2, or a plane. If I have vectors in R3, then I have three options. They're either all on the same line, where they're all the same vector, just multiples of each other. Then my span is a 1D space in R3. If I have two of them that are independent, then my span is a 2D space in R3, or just a plane. And then if all three of them are independent, then it's a 3D space in R3, or all of R3, an entire bubble. And then if I have vectors in R4, don't know why that one's bolded, I have 4 options. Either they're all on the same line and my span is a 1D space in R4, or 2 of them are independent and my span is a 2D space in R4, or 3 of them are independent and my span is a 3D space in R4, or they're all independent and my span is all of R4. So those are my options. So first we need to figure out, first we figure out what space our vectors live in, just literally count however many numbers they have, and then identify how many of them are independent. Generally, if you want to do this, the best way to do it is using rank. Because rank tells you exactly how many linearly independent vectors there are once you find all of your zeros. Okay, so like I said, we want to know what this means in terms of our equations. And that's why this material is very theoretical, because it's harder to think in the theoretical space when you don't have concrete examples to work with. And I've gotten better with it the more I've taught this class. But that's also because I'm reintroducing myself to the material every year. I see a different project every year. I see a different application every year. I'm putting together different equations and systems, and so I have to think about what it means. So if you don't fully understand all the theoretical concepts right now, that's completely fine. Maybe you just memorize that span equation. Maybe you just are memorizing those steps to do, and that's completely fine. But I'm trying, hopefully what I'm saying makes some sense. Okay, so when we have a system of equations, we have 3 options for solutions. We either have one solution, we have an infinite number of solutions, and we have 0 solutions. So those are our 3 options. We can always use Gauss-Jordan and Gauss elimination to solve a system of equations. Generally, we have the same number of equations as we have unknowns. That's not always the case. Sometimes we have more unknowns than we have equations. But generally, we can always write our augmented matrix. We can always plug it in, do Gauss elimination, do Gauss-Jordan elimination, which means we're going to end up with our REF matrix. So here I have 5 matrices. All of these are in REF. They're maybe not in the proper order, but all of these are in REF, and these demonstrate the different options we might have. So here, when I say rank of A and rank of AB, we're talking about this side over here being A, and then all of it together, here we go, this side being A, and then all of it together being AB, my augmented matrix. So if we find the rank of A and we find the rank of AB, or in reality, if you just find the rank of AB, you find the rank of A. So if we start to solve a system of equations using Gauss-Jordan elimination, we're going to end up with different options. That tells us how many solutions we're going to have. If we have 1, an infinite number, or 0 solutions. So here's one instance. I have REF, my lower triangle of zeros. The rank of A is the number of non-zero rows on this side. And we can see I have 3 non-zero rows. So my rank of A over here is 3. 1, 2, 3. 3 non-zero rows if I'm just looking at this side here. If I look at the rank of AB, the rank of AB, same idea, except I'm looking at the entire matrix, is also 3. I have 1, 2, 3 non-zero rows. Given a triangle matrix, I can easily find the determinant. It's going to be 2 times 3 times 1, which is 6. Note my determinant isn't equal to 0. And we can see we can solve this system. And we're going to get a unique solution. We're going to get one solution for this system. If we have at least one solution, then our system is considered consistent. So just some terminology. It's a consistent system with a unique solution. If we look at the second one, do the same idea. Looking at just this side, here's my lower triangle of zeros. Note, I only have 2 rows that aren't 0. So my rank of A is only going to be 2, which means that given this system, only 2 of my equations are considered unique. I only have 2 pieces of information. If I look at the rank of AB, I look at my entire matrix, and once again, I only have 2 rows that are non-zero. So here I have a rank of A, I have a rank of AB. If I look at my determinant, triangle matrix, multiply along the diagonal, my determinant ends up being 0. So as we learned, if my determinant ends up being 0, my equations are linearly dependent. Notice my rank of A is less than a number of equations, number of rows. So there's only 2 pieces of independent information, which means all 3 of them are linearly dependent. And if we look at the system, if we write it out, we can see that we're going to get an infinite number of solutions. So there's an infinite number of solutions. Once again, I at least have one solution, so my system is consistent. So it's still a consistent system, I just have an infinite number of solutions. I only have 2 pieces of information when I need 3. I just don't have that third piece yet. But the other 2 are perfectly fine. Okay, if we look at this next one, it's not in a lower triangle matrix form, but I really would just need to move those 2 equations. I just have to swap those 2 equations. So it really is an REF if I swap those 2. If I look at the rank of A, look at the rank of this side, I end up with 1, 2 rows that are not 0. If I look at all of it, A, B, I end up with 3 rows that aren't 0. Ooh. If I find the determinant of this, I have my 0 row, my determinant's going to be 0. So notice, this is a different set of equations. I have conflicting information here. If I write my system, like if I was actually solving this via Gauss elimination, let me rewrite it out. This middle one would tell me that 0 equals 4. This one would tell me that x plus 2y minus z equals 2. And this one would tell me that 7y minus 4z equals negative 2. 2 of these pieces make sense. This third one, though, tells me 0 equals 4. That's not possible. I can't ever end up with that situation, which means there are 0 solutions. There's no solution. Which means one of my pieces of information in this system is conflicting with the other one. It tells me that x equals 4 and that x equals 2. This can't be the case. I have conflicting information, which means I can't solve this. There's no solution. It doesn't make sense. So here's an example of where I might have no solution, where the rank of A is not equal to the rank of B. So this is an inconsistent system. So those are the 3 scenarios that I might run into. These other 2 are variants on these 3 options. You guys can do them on your own if you want. This one I have 1 solution. This one I have infinite number of solutions. But those are the 3 scenarios we might run into. If we think about all of this in the context that we have, linearly independent, dependent, if I look at this first set, all 3 of these equations are linearly independent. The rank of A is 3. My determinant is not equal to 0. They are not linear combinations of each other. There are 3 independent pieces of information, which means anytime I end up with that situation, I'm going to have 1 unique solution. And it turns out it doesn't matter what B is. B could be all zeros. B could be all the same number. It really doesn't matter. As long as the determinant of A is not equal to 0, as long as the rank of A is equal to the number of equations, I will have a unique solution. If I end up with a situation where I have all zeros all the way across, then that means I have less information than I need to completely solve my system. I'm missing a piece, but the other pieces I'm given are valid. I'm going to have an infinite number of solutions. My determinant of A is equal to 0, but that's okay. I could technically still write this as a solution. It would just be in terms of a free parameter, in terms of an x3. But the two pieces of information I'm given are good. They're good. I just don't have enough pieces. If I end up with a situation like this, where I have zeros on my A side and a non-zero number on my B side, then I have conflicting information. I have information that doesn't make sense, information that conflicts each other. So I'm going to end up with no solution. It's an inconsistent system. Okay, so that means if I know this piece of information, I actually know quite a bit. If I know this piece of information, I know quite a bit. If I know this piece of information, I know quite a bit. If I know this piece of information, then I know quite a bit about what this means. Okay, so we can infer some of these pieces of information if we're given one piece. Yes, there are infinite solutions because one of the determinant is equal to infinity, because we can't find the inverse of A. But note, keep in mind, if I have zeros all the way across, I need to pay attention to whether or not there's a 0 on the B side or if there's a non-zero number on the B side. So you need both of those pieces to figure out if it's consistent with an infinite number of solutions or inconsistent with no solution. Okay, so let's go up to this table that I made here. Not a table, but this nice flowchart that I made that we can use to help give us an indicator, and this will be the last piece we go through, help give us an indicator of what kind of system we might have. So this is a special kind of system where we have all zeros on our B side. This is called homogeneous. Homogeneous. And the reason why we care about that is because a homogeneous system is always consistent, which means there's always at least one solution. We're either going to end up with a unique solution or an infinite number of solutions. So the infinite solution or the unique solution occurs if the determinant isn't equal to 0, if all of my vectors are linearly independent. And it turns out that unique solution is always going to be 0. That'll come into play next week or on Wednesday. If we have an infinite number of solutions, that occurs when the determinant of A is equal to 0 or when the rank of A is less than the number of equations. N is the number of equations or the number of rows. So if we have a homogeneous system, I can follow this flow chart to determine, okay, when might we have a unique solution, when might we have an infinite solution. For a non-homogeneous, or that means our B vector is not all zeros. It could be like 1, 0, 0. Could look like that. That's technically not homogeneous. Then it's either going to be consistent or inconsistent. Inconsistent occurs if the rank of A is less than the rank of AB and the determinant is equal to 0. Consistent occurs when we have a unique solution where the determinant of A is not equal to 0. An infinite number of solutions occurs if the rank of A is less than the number of rows. So we need all of these pieces. So let's say our determinant is not equal to 0. Then that's nice and easy because we're always going to end up with a unique solution. If our determinant is equal to 0, then we also need to pay attention to the rank of A and the rank of AB. Where if we have zeros all the way across, or if we have zeros and then some non-zero number. Okay. So hopefully a lot of that made sense. This is the more applicable piece. But key thing, we need to know how many linearly independent vectors we have. That tells us how many linearly independent equations we have. How many unique pieces of information are we given? Do I have enough to solve my system? Do I not have enough to solve my system? Do I have conflicting pieces of information? All of that fun stuff. Okay, so with that, I will, hopefully all of that was coherent. I apologize for not being perfectly ready, but hopefully all of that was coherent. I'm going to hop over to office hours. If there are any final questions, feel free to ask. If not, I'll see you guys on Wednesday. For the code description in the write-up, is it okay if it's like 3/4 page of bullet? Yes. Bullets are so much easier to read than paragraphs. So if you have 3/4 page of a bullet, that's easier to comprehend than a half page of squished writing. That's perfectly fine. Okay, I will see you all on Wednesday. Have a great day. You can do it. Almost there.